All right, hello and welcome. In this video, we're going to look at this RLC circuit. It's a series circuit that is intended to be a band stop filter. Right, and we see that because our inductor and our capacitor are both on that series line before the output. So whatever we're sending through this, whatever signal that comes in the V input is going to have to go through both the inductor and the capacitor, which we know inductors don't like high frequencies, capacitors don't like low frequencies. So we're going to cut off both the top and the bottom, and we're going to get stuck with this a small band that is being stopped. So that is the intent for this one. So first thing we're going to do is check out our resonant frequency. And so that's our FR equation. FR, and again, that depends on our time constant. That's that 1 over 2 pi for our frequency. Right? And that 2 pi says we're rotating around a circle. The 1 over says we're talking about a frequency and not a time. And then our time constant goes down here, and we see that we have everything in here, right? We've got an inductor, a capacitor, and a resistor. So we're going to use our LC time constant, which is the square root of L times C. So that's our first calculation. So let's do that. We'll do 1 over 2 pi multiplied by the square root of our inductor, which is pretty small, 2.4. So we'll move that down to henries instead of millihenries, so 0.0024, multiplied by our capacitor, which is very small, so 30 picofarads, so 30 times 10 to the pico is negative 12. And that is our answer for our frequency there. So we'll set this equal to 593,135. So we can round that off to kilohertz here because that's what they want. So let's write this whole number in 593,135. We'll move it forward by 3. And this is in hertz. So we'll move it into kilohertz, 593 kilohertz. All right, and that's our first answer here. So 593. After that, it wants us to find our bandwidth. And our bandwidth depends on our Q value. So we'll do that here. Because our Q value needs to be calculated with our circuit components. And so let's start with our bandwidth. Our bandwidth equation, BW, is equal to our resonant frequency, which we just found, FR, divided by whatever our Q value is, and that's our quality factor. So we need to figure out what our Q value is first, and so that's where we are going to start for this calculation. We'll say that our Q is equal to XL divided by our RT, right? Total resistance of the circuit here. So that's important because we have two resistors. We have our winding resistance and our load resistor there. And know that the quality factor does not depend on the capacitor, it depends on the inductor, right? So that's when you got to pick that correct inductor for the circuit you're working with. But we don't know what our XL is, so let's do that first. We'll say XL is equal to, we just got our nice little frequency up here, so we'll plug that in. That's our 2 pi FL, so our frequency and our inductor value. We'll set that into our calculator here. So 2 pi times our frequency of quite large, 59,300. We'll put that whole number in there, or 593,000. And then we'll multiply that by our inductor value. That's one's the small one, 0.0024. That's in henries now. And so now we have a impedance here of 8,942. That's in ohms. And so we could plug that in, just make sure that the resistor and the inductor are in the same notation. Right? So you can't leave this one in kilo ohms and leave the total resistance in ohms. So here we have 8,942 divided by our total resistance, and we know that that is going to be the sum of the resistors that we have because they're in series with each other when it comes to ground. Right? We go through the winding resistance, through all these components, down through our load resistor, and back to our ground and our source. And so that implies that those are going to be in series. And so we will take them in series. So we'll say that it's RW plus the load resistance, so 16 plus 180. And we'll plug that in. So we'll say that we have 8,942 divided by 16 plus 180. That gives us this 45.6. So our Q is equal to 45.6. And that doesn't, it's a factor, right? It doesn't have a notation on the end, so we don't get to identify it that way. But now we can do our bandwidth equation. our bandwidth is equal to our resonant frequency of 593,000 divided by our 45.6. And that's going to give us some kind of frequency output here. 593,000 divided by 45.6. That gets us 13,000. We can round that off. So 13, and it had 3 zeros on the end, so we'll take those off and put a K there instead, and that's in hertz because it's a bandwidth. That's our next answer here. So we can type that in as 13. And they gave us kilohertz on the end, so we'll leave it at 13. And then we just need our output voltage. So in this case, we are at resonance, and we have an inductor and a capacitor in our circuit, and so we expect that to kind of be a linear form at this point, right? Our inductor and our capacitor are going to cancel each other out. We'll just be left with our linear components, our winding resistance, and our load. So we're going to do a voltage divider equation across our load, and that's going to allow us to calculate out what voltage is being dropped across our RW minus what voltage is being dropped across our load. And so voltage divider, want over have, we want the R load, and we have our RW and our R load, and we'll multiply that whole thing by our voltage source to get our output. That's our V out. All right, just our voltage divider again. So this is all linear, so it'll be easier for us. So our load is 180 divided by our 16 for our winding plus our 180 for our load, multiplied by our source voltage of 12. We'll type that in. 180 divided by 16 plus 180, and then that output is multiplied by 12. 11. You can round that off, 11 volts. It's 11.02, but since we keep only 3 digits, that 0 just gets knocked out. And so we'll just say it's 11 volts. So we'll put this in, and we'll check our answer. All right, let us know if you have any questions.